Welcome to part 2 of our lecture video series for Wednesday, April 26th, where we discuss how we can find or calculate the heat of a reaction looking at direct measurements that are made in the lab. And the main means that we have of doing this is using an experimental technique called calorimetry. So you might want to be able to break this word up just to kind of get an idea of what we're talking about. Calor, that sounds like calorie, right? The calorie is a unit of energy. Metry, the process of measuring something, think the metric system. So calorimetry is a technique where we can determine the amount of heat or energy that's exchanged as a result of some process happening in the lab. So this could be, for example, determining the amount of heat that's exchanged between two objects, like if I were to add some hot material to some water and then allow them to come to the same final temperature. If I were to measure that difference in temperature, I could figure out the heat exchange. I could also look at monitoring what's happening with temperature as a result of some chemical reaction happening, or as a result of something changing phase, or as a result of something being dissolved. Point being, calorimetry allows us to determine the heat because we can directly measure our temperature, specifically our temperature change, because recall Q is equal to mc delta T. So if we can get this delta T, then we can ultimately get Q as long as we know the mass and the specific heat capacity of our solutions or substances. I should be a little more generic. So calorimetry, the main ideas about calorimetry is that we capture some kind of system that is going to involve some delta T in an insulated but non-constant volume, just constant pressure. So insulated material at constant pressure. There is a system of calorimetry where we can look at fixed volume calorimetry. That's called bomb calorimetry. It's what's used by the FDA to determine like the caloric content of your food. That is not a technique that we have access to in Chem 210, so you will hear about it, learn about it in your future chemistry classes, should you choose to take them. But in general, when we're talking about calorimetry, we're talking about constant pressure calorimetry, because if that is true, meaning if our reaction or our system or our change is happening at constant pressure, then once we find that heat, we've found the enthalpy. So that's kind of the reasoning there. So in calorimetry, we are looking at a system that's in some insulated material. This is going to allow us to assume that there is no or minimal heat exchange between the system and the surroundings outside of the container. So when we do calorimetry, coming up next week, we are going to be using insulated material that is just styrofoam coffee cups. And we are going to assume that if there's any kind of heat absorption by our system or heat release by our system, that is purely going to be an exchange that's happening between the actual chemical molecules that are the reactants and products and the solution environment that those chemical molecules are found in, right? Something that we do have to kind of pay attention to, and we'll talk about this more in lab, is we have to note that while the calorimeter, this insulative material, allows us to assume that there's no heat exchange between what's going on in our solution with our molecules, etc., within the cup itself or within that insulated system, that doesn't mean that the cup or the insulated material that our reaction's being performed in doesn't also exchange heat. So note, we may have to consider any kind of heat exchange with the insulated material. Because while something like a styrofoam coffee cup, especially two of them, is decently good at insulating, that doesn't mean that they don't absorb like anything, right? They do absorb some minimal amount of heat if there is heat being released by our system. So we do have to account for that. We will worry about this when we talk about like how to do this in the lab, like when we practice and apply this experimental technique. But for now, what I want us to do is I want us to look at an example of how to calculate the heat of a reaction from experimental calorimetric data, meaning experimentally determined changes in temperature. So let's determine the heat of a reaction for the precipitation of magnesium carbonate from the reaction between sodium carbonate solution and magnesium nitrate. Solution. All right. I think it is always very helpful to write out the actual chemical reaction that's happening here. So we've got our molecular reaction, which is looking at magnesium nitrate solution reacting with sodium carbonate solution. This is going to undergo a double displacement, right? We were told that a precipitate is formed. Precipitation is just another version of a double displacement. This is going to create sodium nitrate, NaNO3, which is soluble. All nitrates are universally soluble. And then the provided magnesium carbonate precipitate. And to ensure that we are balanced, let's see here, we've got 2 nitrates, 2 sodiums on the reactant side, and yet we do not have that on the product side, so we need to double this. All right. Now, let's see here. Let us figure out how we might, oh no, I need to give some more data. How we might figure out this heated reaction given the following information. So in the lab, we know a couple of things. So we knew that, let's see here, 25.0 milliliters of a 2.0 mole per cubic decimeter. I know that's not molarity, I'm sorry. Let's see here what solution this is. This is my magnesium nitrate. Solution that is mixed with, let's see here, another 25 milliliters of same concentration of our sodium carbonate. And a temperature change from the initial solution temperatures of 25 degrees C to a final product temperature of 19 degrees C. All right. So what on earth's going on? There's a lot of information here. So we are trying to determine the heat of reaction. And remember, the heat of reaction is typically the amount of heat that is exchanged from our system in its surroundings as a result of some chemical reaction occurring, expressed per mole of product. So if we are going to figure out things like the heat from masses, things like specific heat capacities, and things like our change in temperature, and we want to find the heat of reaction, we're also going to need to find the moles of product. So this is kind of another task on our to-do list here. All right. So let's see here. How do you guys want to do this? We could break this up a couple of different ways if you want. Let's see here. Let's start by writing out the following, diagram. So let's kind of look at what's going on in the beaker. Always a good idea to think about what's going on in the beaker. Okay, so it looks like I have mixed 25 milliliters of my magnesium nitrate solution with 25 milliliters of my sodium carbonate solution. So this was 25.00 milliliters. Added a sig fig here, 25.0 milliliters. And that results in us having some new final solution where we've got our spectator sodium and nitrate. And then we have our solid magnesium carbonate. Okay. Let's think about what else is happening. So let's describe system and surroundings here. So the system is going to be the reactant particles, right? These are the things that are actually undergoing some kind of chemical change, which means that the surroundings is going to be the solution environment in which those reactant particles are found. So to be a little more explicit about this, This system, our reactant particles, are the reactants that are involved in the actual formation of our product. This would be the magnesium and the carbonate, meaning that the surroundings is going to be the solution around those particles that are coming together, and that solution is the things whose temperature we are monitoring when we are undergoing our calorimetry. So we have some initial temperature here of our solution, which was given at 25 degrees Celsius. And then we have some final temperature of the solution, which was 19 degrees Celsius. So what we know is the solution environment had a change in temperature of 25 degrees, of 19 degrees Celsius minus 25 degrees Celsius. So final minus initial. This is talking about the solution, right? If you think about a thermometer being placed inside our system or inside our little calorimeter, right, our little insulated container, then what you would see is that we're looking at what the surrounding actual solution is absorbing or releasing when it comes to heat, or how that temperature is changing. So since I know about the solution environment, specifically the change in temperature of the solution environment, then I can figure out Q solution. So Q solution, how would I figure that out based on what I know about how to find heat? This must be the mass of the solution times the specific heat capacity of the solution times delta T solution. And I know the temperature change of my solution, right? I already have that over here. This is -6 degrees C. So that means that I need to find the mass of my solution and also the specific heat capacities of my solution. Now, if I wanted to be really, really technical and, kind of, I guess technically correct, I would need to figure out the mass of the solution by looking at the masses of each of my reactant solutions and use their relative densities to figure out what's going on to get my masses from their volumes. But if you'll notice, in all this information I gave you, I told you volumes and I gave you concentrations, but I didn't give you any kind of density. So we can't directly get like mass and volume knowing the exact density of the magnesium nitrate and the sodium carbonate solution. So if we're going to try to get mass, then we're going to make a couple of assumptions. The first is we're going to assume that each reactant solution has a density that is same-ish to the density of water. So we're going to approximate the density as being 1.00 grams per milliliter. So that takes care of our mass of solution. We can get the density from our total volume of solution. Sorry, we can get the mass from the total of our volume of solution using our density. Okay. We also do not know the specific heat capacity of our reactant solution, or the solution, I should rather say, that's surrounding our reactant particles, the system. So since we weren't given that, we're also going to assume, since this is an aqueous reaction, that each reactant solution has a specific heat capacity that is basically equivalent or approximated to be equivalent to the specific heat capacity of water, which is 4.184 joules per gram degree Celsius. Okay, and then delta T, that we know, at least that's something we found. Right, the change in temperature of the solution, that is exactly what was directly measured in the lab. Now, just kind of beware. These assumptions, while useful for now, are not always going to be ones that you can make, meaning I might give you or make you calculate the actual densities of your reactant solutions, and I might also give you their actual specific heat capacities. But for now, this assumption's fine. So let's see if we can't figure out what's going on with the solution. At least what's going on with the heat that is being changed, meaning absorbed or released by the solution surroundings. So Q solution, that's going to be the mass of our solution. So let's look at this reactant solution. The total volume is 50 milliliters, and if the density is 1 gram per mil, that means that I have 50.0 grams of my solution. I've also said that the specific heat capacity could be approximated to be that of water, so times 4.184 joules per gram degree Celsius, times R delta T, -6 degrees Celsius. And this should be, there we go, okay. So let's figure out what this is. So when I do this, I get, without rounding, let's check, 50 times 4.184. So without rounding, this becomes negative 1255.2 joules. So let's think about what this is saying. This is saying that the solution, aka the surroundings, so let's maybe be a little more clear about that, are releasing heat into the system of reactant particles, meaning that our reactant particles is absorbing all of the heat that was released by our solution that is surrounding us. So the heat of the reaction or reactant particles is the negative of the heat that we get released. No, 1255.2 joules. So this becomes positive. Meaning that our reactant particles are absorbing 1255.2 joules of heat. All right, I'm going to break this up into two parts because now that we have information about our system, right, we know how much our reactant particles have absorbed in joules. We need to now figure out how much heat has then been absorbed per mole of product. And in order to figure out the moles of product that are made, we're going to have to do some stoichiometry. So in part 2 of this lecture series, we will continue on with this example, determining the heat of reaction empirically by looking at how many moles of product are made.